All right, so yesterday we went over graphing. Okay, I showed you how to build a line graph on Google Sheets. Okay, we talked about how you do slope calculations. We looked at how you use y equals mx plus b. Okay, and those are skills that we're going to be building on and using here in the coming weeks quite a bit. What we need to go over today is the two types of graphs that we're going to deal with most often, or at least most often in the first part of this unit. Okay, in terms of kinematics. Okay, what kinematics is the study of the movement of objects. Okay? So we're going to be looking at things that are traveling at constant velocity, constant speed, okay, displacement, time, okay, that kind of stuff. So the two kind of graphs that we're going to look at will be position versus time graphs that tell us where an object is at various points in time, and velocity versus time graphs that tell us how fast the object is going and in what direction at various points in time. Okay, everybody follow me there? So those are the two main graphs we're going to be looking at. Your responsibility will be, or the expectations for you will be, that you'll be able to look at either of those graphs and tell me what's going on in that graph, like describe it to me, and that you'll be able to perform some simple calculations from those graphs. Okay, so we'll go over all of that stuff today because that'll be important for the position versus time graph lab that we're going to do tomorrow. Okay, so we need to understand what information can be read from the two types of kinematics graphs, and we said those two types are position versus time and velocity versus time. Okay, understand that graphs and equations, and I still haven't given you guys a formula sheet, I apologize for that, but we haven't needed it yet. Okay, equations from kinematics show the same information in different ways. Okay, and learn that kinematics equations are derived from graphing. Okay, so when you get your formula sheet, kind of the two main ones will be your v equals d over t, okay, and this other one here that we haven't talked about yet, which calculates acceleration. Okay, those will be kind of the two that are important for the two types of graphs that we're going to be going over. Okay, questions on what we'll be looking at today? Vf minus Vi over t. So final velocity minus initial velocity over time. No, the F and the I are subscript. So it's like I always stands for initial, F always stands for final, right? And then they go subscript after whatever they go with. So final velocity could be, I could have on the bottom here, I could also be saying final time minus initial time, but we don't really ever say that. We just say how long, right? Okay. So on a position versus time graph, okay, specifically for position versus time graphs, okay, they are used to show or to represent the location of a moving object over the course of time. They tell us where the object is or was at various points during its movement. Okay, so if I'm looking at, let's say, this first example here as a position versus time graph, what is this first part of the graph saying the object is doing? It's not moving, right? Okay, how do I know it's not moving? It's flat and its position is, it's not changing, right? It's 20 at the beginning of this, it's 20 at the end of this, it didn't go anywhere, okay? So anytime you see a horizontal line on any kind of graph, it means that something isn't changing, okay? The manipulated variable that's running along the bottom is changing, but the responding variable is doing nothing, okay? In this case, the object's not moving, all right? Everybody follow me there, okay? What about the next section of the graph? What's going on in this part? Okay, how is it moving? It's moving further away from us, or it's moving in a positive direction. Okay, how do I know that? Well, its position is becoming more and more positive. Okay, it's moving farther away. How is it doing that? Is it doing it at a constant speed? Is it accelerating? It's doing it at a constant speed. We always want to say accelerate anytime we see an increase, like, oh, something's changing, something's going up, accelerating. Except that actually this is showing the object traveling at a constant velocity in that direction. Here's how I know. If I look at this first square, how far did they go? 20 meters. How long did that take? 1 second. Same here? Yeah, okay. In both of those squares, they went the same distance in the same amount of time, which means they were going the same speed. They were going at a constant velocity in a forward direction. Okay, and that's how, if I was asking you on a test, describe what's going on in like A, B, C, and D. Okay, I would say in A, you could say the object is standing still. In section B, the object is moving at a constant velocity forwards. Okay, or in a positive direction. Or maybe it would give you on here, and lots of times it does, it would say, it would give a direction like north. Okay, something you have to look for on the axes sometimes. Okay, for part C, what's going on in part C? It's not moving, right? Okay, and for D, what's it doing? It's coming back, right? It's turned around and now it's moving backwards, okay? Or it's moving at a constant velocity back towards its starting position, or in a negative direction, you could say, all right, something like that, okay? And how do I know it's coming back? Because it's coming down, and it actually ends up back at 20 meters, okay? So that's one of the things I would ask you to do with a graph, is to interpret the graph. That is, look at the graph and say, here's what's going on, right? That would be kind of the sort of basic level of understanding of graphs that's expected. The next thing that would be expected would be, show me some calculations from these graphs, right? So what if I asked you, what is the displacement of this object over the entire trip? It's 0. How'd you figure that out? Right. It goes back to the same position it started from. Well, guys, that's because displacement is calculated by going final position minus initial position. So at the same position, then the displacement is 0. Okay. What if I asked you, calculate the displacement of the object between 0 and 3 seconds? Not just 20 meters, it would be, and I asked for displacement. Okay, I took the north off of here, but yeah, if the north was still on there, it would be north. If there's no north on there, you could say forwards. Okay, you would have to then come up with a direction that makes sense. Okay, forward or positive are kind of neutral directions that you could use. If there's no north on here and you say north, it isn't right because it doesn't specifically say north. But in this, forward or positive can be implied. Okay, does everyone kind of follow me there? Most of the time a graph won't do that. Most of the time on a graph you'll get like positive signs beside these, or they'll be north on the axis or something like that to give you the direction. Always look for that. If there's a common mistake that causes people to lose marks needlessly, it's failure to look at the axis to get a vector. Okay. All right, what if I asked you to calculate the average velocity between 0 and 3 seconds? How would I calculate the velocity, average velocity between 0 and 3 seconds? I would do v equals d over t, right? Okay. You guys just told me that the displacement between 0 and 3 seconds was positive 40 meters. Okay, and you did that by going 60 minus 20, final position minus initial position. So we'll write the whole thing that we did here. Okay, so we would go positive 60 minus positive 20, okay, over 3 seconds. So that's positive 40 over 3. Okay, and was it? Yeah, 2.3 repeating? No, 23. Let's just figure it out. Yeah. There you go. 13.3 meters per second, also in a positive direction. Okay, so the formula that we were using on that worksheet for all those word problems still applies to graphing. Okay, because really, what's a graph except a visual representation of one of the word problems that we've been doing? Okay, that's really all a graph is a visual representation of a word problem. Okay, another thing that you might be asked to do. What is the total distance traveled in this graph? Okay, let's check it out. How far do I go here? 0. Okay, how far do I go here? 40. Here? Here? Okay, 80 meters. Okay, total distance is 80 meters. Remember, distance doesn't care whether I go forward or backward, just how far did I go. So I would have to figure out how far it went in all the sections and add them up. Whether they're positive or negative, add them up. Okay. What's the average speed over the whole trip? Okay, do I do this again? Right, except now it's speed equals distance over time. Okay, so it's really nothing new. There's not like any new formulas or really new calculations. It's just how do I get the data that goes into that? Okay, well, I interpret it off the graph. So 80 over 6. Okay. So we're looking at, because of course it was double. Yeah. Okay. Yeah. More coffee. Meters per second. Okay, 13.3 meters per second. Okay, but again, this time I don't have a direction on that, right? There's no positive sign on that because speed is scalar, right? Okay, it doesn't have direction. All right, what is that other graph showing? That is what the position versus time graph of an accelerating object looks like. Okay, how do I know it's accelerating? Okay, it's a curve, and I can just memorize that curved graphs are always accelerating, except that that's only true for position time graphs. But the other part of it is I can look at it logically. Okay, in the first second of travel, this object did not go very far. Okay, but in the next second, it traveled further. Okay, so if I'm looking at, in the first second of travel, the object's position only changed by that much, that little tiny green line. In the second second of travel, it changed by that much. In the third second of travel, even more and more and more. The only way that you go further in the same time interval is to be going faster. Okay, so this is showing an object whose velocity is increasing because they're going further each second than they did the second before. Okay, everybody all right with that? Okay, so again, that's an interpretation thing, and it would be very easy for me to ask you, on a test, explain what's going on in this graph. Okay, and if you said accelerating object, you'd get like 1 out of 3. Okay, you would say accelerating object because the distance traveled or the displacement in each second is getting larger than it was before, showing the speed's increasing. Something like that is a kind of a more thorough explanation than just accelerating. Okay, if it was a 1-mark question, accelerating would be good enough. Okay, like maybe on a quiz. All right, questions on the position versus time graphs? Awesome. Well, actually, figuring out how far something travels, even when it's a curve, isn't any different, right? It's just, okay, well, here's their position. Their position is 9 meters. Well, between 0 and 2 seconds, their displacement was 9 meters forward. Just because they're accelerating doesn't change how far they went. Okay, sorry, I'm missing where are you asking about this graph? Okay. Oh, down here? No. No, I would never give you a graph where it was ambiguous to know where the object was. No, I would never do that because that's not fair. Then it becomes an interpretation thing. And it's very difficult to make a key when interpretation comes in. Well, I mean, you have to do that in English, I guess, all the time, which is why I don't teach English. Okay. Because we did this reading comp thing in CLCs the other day, and like I got one of the best scores. I got 4 out of 7. Okay, on like reading this poem and being able to say what it said. I'm like, but that answer seems right to me, but it's not right. Well, who are you to say that? Right? That's how I interpreted the poem. Like, yeah. Well, but see, that's why I deal with concrete things in science, right? And not that I don't like reading and like literature, but I don't like the whole interpretation of it. Like, what was this story about? A guy in the woods. No, it was about all of this other stuff. Yeah, I totally didn't get that. It was a metaphor for this and that. I read a story about a guy in the woods. Yeah. Yeah. He went to the University of Alabama. I don't know. Like, yeah. Yeah, I guess I missed that part too. Okay. Bit of review from yesterday now that we don't want to be interpreting things anymore. Okay. Slope calculations. Okay. Yesterday we said you can calculate slope by doing rise over run. Okay. So that would be on a position versus time graph. That would be the rise would be the displacement, the change in position. Okay, the run would be the change in time. And the same is true when you manipulate y equals mx plus b, because you go y minus b over x. Okay, well, this would be b right here. Up here would be like y. Well, y minus b would be the change in displacement, and x would be the change in time. Okay, so the slope of the line on this kind of a graph represents the velocity. Okay, because it represents the rate of change of position. Right? That isn't something I expect you to memorize. Okay, a lot of people are like, "Oh, I'll just memorize it. The slope on a position time graph is velocity, and the acceleration, or the slope on a velocity time graph is acceleration. I'll just memorize that." That'll get you through Science 10. But you get to Physics 20, and we deal with about 24 different kinds of graphs. And then you go on to Physics 30, and you are actively taught close to 40 different kinds of graphs, and then we have seen up to another 10 show up on a diploma exam that we didn't even cover. Okay, and it's just because they're wanting you to show your ability to interpret any graph. Well, it gets pretty hard to memorize a graph you've never seen before. Okay, so it's important for us to be able to look at a graph and say, all right, I've got position over here, and I've got time here. Well, if I find the slope of this line, that'll be the rate of change of position. Oh, the rate of change of position is velocity. Boom. That shows a better understanding. Okay, that shows that I can look at this graph, see what's on it, and figure out what's going on. Okay, if I'm calculating the slope, I'm calculating the change in this over the change in that. Well, that represents this. Okay, looking at your formula sheet. It's better to do that because it's less memorizing. Okay, and it's a skill that is transferable to basically any graph.
What is a slope like measured? Because last class we did that one with pi.
Yep.
And there's 3.14. Is that like degrees?
No, it had no units. Pi has no units. Okay, because when we did that graph, we divided centimeters by centimeters, right? The circumference is measured in centimeters, the diameter is measured in centimeters, so there are no units for pi.
Or, but I mean, like, the slope, what's the slope of the graph?
It depends on the graph. Okay, so here's where I'm going with that. This graph, the slope of this graph will be in meters per second.
I kind of get that. I mean, like, when you say, if I said the slope of a graph, like another graph, the slope of the graph is 3.14. Oh, you're so, oh.
It depends on the graph, right?
So
Like,
it has nothing to do with like angles.
no, it has nothing to do with angles. I mean, the slope, the number you get for the slope has to do with how steep it is. But no, like we never deal with degrees on a graph. Yeah, no, we never do that. Okay, and the slope of a graph represents different things depending on the graph. Yeah, like we were talking about yesterday, you know, we had a graph that was like this, right? Like the value of shares, right? The stock market versus the time that Trump has been president-elect, right? And we were saying, well, the slope of this would be dollars per week. Okay, it would be negative dollars per week, but it would be dollars per week. Okay, whereas this one here is going to be meters per second. Okay, and on a velocity time graph, it'll be meters per second, which is a rate of change of velocity. That's what acceleration is, and so on and so on. Okay, so every graph, the slope represents something different. And it's really, once you get the hang of it, it's not that hard to figure out what it is. Because I'm never going to give you a graph that you've never associated those two things together before and go, hey, figure out what the slope is. Well, you'd be able to give me the number, but probably not be able to tell me what that meant. Like, I just did this with my Physics 20s the other day. They did a graph of the effect of normal force on the force of friction. Okay, you guys have never seen something like that before. Okay, the units on this side are newtons, and the units on this side are newtons. What are the units for my slope? It doesn't have any units. So now you look at that and go, all I know is the slope is this number and that it has no units. I have no idea what it represents because I've never been taught the relationship between these two things before. Okay, what my physics 20 kids know is that the force of friction is mu times the normal force. So when they found the slope, they realized they were finding this, which is called the coefficient of friction, how sticky two surfaces are. Okay, so it's tough to interpret a graph you've never had any experience with, because if it comes out to no units, you're like, there it is. I have no idea what it means. Right? It's okay. You didn't have to follow that. We did physics 20. I was just illustrating another graph where you'd end up with a slope with no units, but then you'd go, I don't know what to do now. So you were supposed to get to the I don't know what to do now. That was what you were supposed to arrive at. Okay, so back to this. When we have the slope on a position versus time graph, we're finding the rate of change of position, displacement, over the rate of change of time, which is always the same. Okay, and we're going to get velocity out of that because it's going to be in meters per second. Okay. Okay. What's going on in part A of this graph? Moving forward at a constant velocity. Okay, like if I was giving you this on a test, you would, to get full marks, you would have to say moving forward at a constant velocity and not at a constant speed. Why would constant speed not be acceptable? Because you told me forward, right? Speed's a scalar quantity, not specific enough. Okay? Or if you just said moving at a constant speed, not specific enough. This graph has a positive and negative part to it. Okay, you should definitely be talking about vector quantities. Austin. You could. That would be even more specific. Like if I just asked what's going on or describe the motion is probably how I would word it. You would say moving at a constant velocity forwards. I might then ask you how far did it go in part A? And you would say 6 meters. Why wouldn't you say 6 meters forward if I asked you how far it went? Right? How far is distance? I would probably not use that term on a test either. I would probably say what was the distance traveled? What was the displacement? So you would calculate the right things. Okay, part B, what's going on? It's stopped, right? It's not moving. Okay, what's going on in part C? Okay, it's going backwards. Okay, at a constant velocity, right, or at a negative velocity, right? In part D, it stopped. Part E, okay, it's going forward, forward again. Okay, and F, also going forward. Where is it going faster, E or F? E. Okay, how do I know it? Okay, going farther in a shorter time. Yeah, I guess it goes 6 in E, doesn't it? Okay, I would also say you could be as simple as it's steeper, right? That tells me I recognize slope is the speed or is the velocity on this graph. So steeper line means faster. All right. What's the total displacement over the whole trip? 0. Okay, starts at position 0, ends at position 0. Okay, and there's actually a little part right here, okay, that is flat that goes all the way to 18 seconds. Okay, it doesn't really show up very well. Okay, what is the displacement in part C? Part C goes from here to here. You're on the right track though. You did the right math with the wrong numbers. Okay, it's 16, but let's look at how we do that. Remember, displacement is our final position minus our initial position. Since we're only dealing with part C, our final position is minus 10 or negative 10, okay? And our initial position is positive 6. Well, negative 10 minus positive 6 is negative 16 meters. Okay, that formula will always work, right? And it's quicker than trying to go, okay, so it was at 0 and it's at 10, all right, just put in, okay, my final position is 10, initial position is 6, subtract them, you're done. Okay. All right, what's the velocity in part C? Yep, negative 4 meters per second or 4 meters per second backwards. Okay, either one will be acceptable. How did we figure that out? V equals d over t. We just calculated what d was. It's negative 16 meters. Part C runs from 6 to 10 seconds, which is 4 seconds. 16 over 4, 4 meters per second negative. Okay, everybody with me on that? Right. So really, again, it's just like the word problems we've been doing, except you're getting your data from a graph rather than from a paragraph. Okay. All right. What is the total distance traveled? For the whole trip? Yeah, I think that's it. That's what it comes out to. So in part A, I go from 0 to 6. I don't go anywhere in B. We just figured out that C is 16. Don't go anywhere in D. Go from negative 10 to negative 4. So 6 and then another 4, or sorry, another, 4 here. Okay, so we got 10, 26, 32. Yep. Okay, 32 meters is the total distance traveled. Okay, everybody following how those kinds of calculations would go?
I thought C was negative.
I asked for distance. Distance is scalar. I only need to know how far I went, right? You're right. The displacement in C is negative 16 meters. But because I asked for the total distance traveled, I add them all up regardless of their direction. The slope will be negative for sure. And yeah, I mean, your change would be negative. Whatever is changing in a negative way because it's getting smaller. Okay, any other questions on that one there? Okay, so guys, that actually was on a unit exam like 5-6 years ago. I had that question on there, and those are the kinds of things I asked. Describe what was going on, and I picked a few of the sections at random. I asked which one was the object going faster, E or F. I asked for a total distance traveled. I asked for average speed. I asked for average velocity between two segments and things like that. Okay, exactly the kind of calculations we've just gone over. Right, so those would be the kinds of things you'll be asked to do on a test. Okay, what's going on in this graph? Yeah, in fact, there's a lot of changes in velocity on this graph. Okay, in the first part, the object is accelerating positively. It's getting faster and faster and faster until you get to about here. Okay, and then it starts to what? Okay, so is it speeding up or slowing down? It's slowing down. How do I know that? Look at the curve. Is the curve getting steeper or flatter? Flatter. In fact, at B, it's flat. And now it's doing what? It's accelerating. Okay, it's getting steeper, right? Right after B, right after this point right here, that curve gets really steep really fast, right? And then when it gets to about this point here, the curve starts to get flatter, which means this object is now doing what? It's plateauing or slowing down, okay? In fact, by the time it gets to here, it's pretty much what? Stop, because the line is flat again. This is a graph of this. Oop, that's a terrible catch. Okay, the first part is me actively pushing the marker up in the air. I'm accelerating the marker. As soon as it leaves my hand, right there, it starts to slow down. As soon as it leaves my hand, gravity grabs it. Okay, well, not that gravity wasn't grabbing it before. Okay, but because I'm not pushing it anymore, gravity becomes the only force acting and it starts to slow down. Okay, that's why it eventually comes back. Okay, so when it reaches its highest point, it's actually momentarily stopped. Okay, so at its highest point, it's stopped momentarily. Okay, at the very top. That's where it turns around and comes back down and accelerates at exactly the same rate on the way down. Okay, gravity can only accelerate things at one rate. Incidentally, that rate is 9.81 meters per second squared. Okay, then at this point is where I catch the marker. So I'm catching it, I'm slowing it down and stopping it. Okay, that's what this graph is of. It's still stopped.
No, but I'm saying like if it's just like you're hit something then it would just be like flat after it.
Yes, it would be flat. Yeah, regardless of it stopped one way or the other. Whether I caught it, the reason I'm saying I caught it here is because this is a slow curve. If it had hit something, it would be like it would like flatten right away, right? It'd be stopped. Its acceleration would be much greater at that point. You're not going to eat that after it's been on that dirty desk, are you? Yeah. Yes, this is saying it is saying that yeah, I caught it at a higher height than I threw it from. Yeah, that's a good observation, right? The initial position is like down here at position 0, and I caught it up here by my shoulder instead of by my waist. Yeah.
It's also saying that you sort of 8 meters.
Yes. Yeah. It's a little artificial, but yeah, it wasn't really of me throwing something up in the air, but it's of that kind of a motion, right? Okay. Now, what this is also showing us is something you're rarely asked to do in Science 10, but it's something you still need to know how to do. And that is, once in a while, you'll be asked to calculate the instantaneous velocity of an object. Okay? Now, most of the time, that's easy because it's the same as the average velocity as long as the object is traveling at a constant velocity. In this case, though, we know the velocity is doing what? It's changing. So it might say, calculate the instantaneous velocity at point A. Well, I can't just go, all right, well, 0 to there, make a line and calculate its slope, because that does not represent what's going on here. Okay, and that number will be probably larger than what it is at A. So in order to do that, you've got to understand the only thing I understood in university calculus. It was the first day. After that, I understood nothing. Okay, and I passed, which is really scary. But what I learned that first day in calculus is that a curve is an infinitely large number of infinitely small straight lines. Okay, it's like if you look at a picture in high res and low res side by side. Okay, what can you see in a low resolution picture you can't see in a high resolution picture? You can see the pixels. Okay, you can see the little squares that a computer uses to build an image. Okay, well, a curve is really just a high resolution picture of a whole bunch of really small straight lines that are getting steeper and steeper and steeper and steeper, but they're all attached. Okay, everybody follow me there? So what that means then is there is an incredibly small, infinitely small straight line that exists at point A. Can I calculate its slope? Well, I can't if it's infinitely small. How can I make it long enough to calculate its slope? Okay, take your ruler and like, yeah, okay. What do you call a line that touches a curve but doesn't cross it? Starts with T. A tangent line. So you draw a line that is tangent to the curve at A. Because if it's tangent to the curve at A, it's parallel to the little tiny line at A. If they're parallel, they have the same what? Slope. Okay, so what you're doing is you're drawing a tangent line to essentially extend this infinitely small line that exists at point A, making it long enough to do a slope calculation, either a rise over run calculation or a y equals mx plus b calculation if you're lucky enough to get a y-intercept out of it. On this graph, we won't get a y-intercept because it's down below 0. It's a negative number, and our graph doesn't go down there. Okay, so we don't necessarily know what it is. Okay, so to do that, you take a ruler, usually if it's on paper, which is why it's not something you're going to be asked to do very often. Okay, and you draw a line that is tangent to the curve at point A. Now, it should be long enough for me to get 2 points off of it that I can use in a rise over run calculation. So I think I can use that one, and we'll use that one. I could use this one too. Doesn't matter, it'd come out the same number. Okay, so my rise and my rise is going to be 10 minus 2, so my rise is going to be 8 meters, and my run is going to be 17 minus 6, so 9, 11, sorry. Okay, so 8 over 11 has to be on. I don't know why this calculator needs to turn off for battery saving because it doesn't have a battery. But anyway, okay, 0.73 meters per second would be the instantaneous velocity, positive 7.73 meters per second at that point. Okay, everybody with me there? Okay. Again, it's not going to be something you're going to be asked to do. All it really tells us is, do you understand that when you calculate the slope of a line on this graph, you're calculating velocity, okay? And that a curve tells you the velocity is changing. Now, I want to calculate the instantaneous velocity at point B. Now, we just said what was going on at point B a minute ago. It's flat, right? It's stopped at point B. Well, that's true because if I draw a tangent line that just touches the curve at point B, it's kind of flat. It doesn't have a slope. Okay, so that's why this works. Okay, that's kind of your proof that this whole tangent line thing isn't full of crap. Okay, is that when you do that, it clearly shows that at that point it was turning around. Okay, so next kind of graph, velocity versus time graphs. So velocity versus time graphs will show us the same movement that a position versus time graph shows, but shows it from a different point of view. Okay. These two graphs, the one on the left here is a position versus time graph, and the one on the right is a velocity versus time graph. Okay, they are showing the same movement. Oh, undo. Not what I wanted either. That thing, that I want to go away. Okay, they are showing the same movement. Because the position versus time graph is just a diagonal line, which means the object is traveling at a constant velocity forwards or at a positive constant velocity. Okay, what's this velocity versus time graph showing? Right, it's showing something moving at a constant velocity because the velocity is not changing. It's a horizontal line. Okay, everybody with me there? This is why on a test you really got to look at what kind of graph is in that question. Because if you look at this without looking at the y-axis, you might think, oh, position time graph, not moving. That was easy. D, not moving, except D's not right. Okay, it would be A, moving at a constant velocity forwards because this is a velocity versus time graph. That is a very common mistake that people make. They don't look closely enough at what kind of graph is in a question. Okay, according to the velocity versus time graph, about how fast is this thing going? 260, yeah, it looks like about 260 meters per second, somewhere in there. Okay, that's what it says on the velocity versus time graph. Can I confirm that with my position versus time graph? Yep. Okay, how do I do it? V equals d over t, which will indirectly be the slope of this line. Okay, so that'll be 1400 minus 100. Okay, so the rise of this graph will be, okay, or y minus b. The y-intercept is 100. Okay, so 1400 minus 100 over x, which is 5. Okay, so we'll just write that in here. So y minus b over x is going to be 1400 meters minus 100 meters over 5 seconds. Okay, 1300 over 5 should be 260, right? Okay, so they're showing the same movement. They're showing an object traveling at 260 meters per second. Okay. What's the acceleration of that object then? 0. Acceleration is a change in velocity. The velocity is not changing, therefore the acceleration is 0. Okay. According to this graph, what's the displacement of this object? 1,300 meters, right? It goes from 100 to 1,400. That's positive 1,300 meters. Okay. No, that's just a line to show D. Nothing could do this. Okay. This line here represents a physical impossibility, traveling negative 1,300 meters in no time. Okay, so you've broken a law of physics if you did that. Okay, that's just a reference to show you it ended at 5 seconds. Okay, how would I go about calculating the displacement of the object using this graph? Actually, I can. V equals d over t. Okay, I can still use v equals d over t. I know v is 260 because I can read it right off the graph, and I know that the object travels that for 5 seconds. So I can go 260 times 5 and get 1,300 meters forwards. Okay, essentially, I just calculated the area of this rectangle, agreed? 260 times 5, base times height. Okay, remember that, because that's how you calculate the displacement on a velocity time graph. You calculate the area between the line and the x-axis, and it'll always give you the displacement. Well, a speed over time graph would look just like this without the positives. Yeah, so there'd be no negative part. A velocity time graph is usually what we use because it then takes into account something could move backwards. All right, so let's say, I'm going to put that line back on here. What's that object doing? It's increasing in velocity. In other words, there's a change in velocity, so that object is accelerating. Okay. A few minutes ago, I showed you this formula. Acceleration equals final velocity minus initial velocity over time. Okay. You might notice that that's kind of similar to how you calculate velocity. Final position minus initial position over time. And off of this graph, that was the what of this line? The slope. So would the slope of this line then give me the acceleration? Yes. Okay. It tells me the change in velocity over time. Okay. So the slope of that line will be acceleration. Okay. Because really, if I'm translating this in, it would be y minus b, because this would be vf, this would be vi, but it would also be b. Okay. This would be y. Okay. And then this would be the time, which equals x. Okay, because it's on the x-axis. So I'm going y minus b, okay, over x. Everybody follow there? So remember, one of the first points that we talked about, it was in your key points, that equations that we use are derived from graphs. This equation is derived from the slope calculation of this graph. V equals d over t is derived from the slope calculation of a position time graph. Okay, we derive all of our formulas from graphs. All right. For that diagonal line, how would I calculate the displacement of that object? No, that won't help me find the displacement. Right. I'll find the average velocity and multiply it by time. Okay, remember that average velocity equals total displacement over total time. Okay, if I want to find the total displacement, I take the average velocity and multiply it by t. So this thing increases in velocity from 100 to 550. Okay, so would its average be kind of halfway in between that? Exactly. It would be exactly halfway in between that, because for half of the time it's going faster than the halfway point, and for half the time it's going slower than the halfway point. All right, so really then, if I find the area of that triangle, will that be the average velocity over time? Because it'll be base times height divided by 2. And the height divided by 2 is the average velocity of the object. You get it? Good, it's the first time for everything. Most people just stare blankly and go, no, so that's good. So what we're doing here is we're just saying that, okay, the halfway point would represent average velocity. And then I'm manipulating this equation, VAV times T equals D. Okay, in other words, I'm finding the area underneath that line. The same way we did when it was a rectangle. We took the average velocity. It was just easier to calculate the average velocity because it was that number, it didn't change. Awesome. the halfway point between 100 and 550, right? The height of this graph is 450. Yeah. Right. So half of it is 225. Right? Yeah. Okay. Everybody follow me there? Okay, good. Okay. This is a graph of a person running a race. Okay, probably like about an 80-meter hurdles race or so. Okay. What are they doing right here in this first part? They're accelerating. And then right here, they're still accelerating. Difference is the acceleration here isn't uniform. The acceleration here is uniform. That means that during this part, their velocity changes in a way that's not like it goes from 1 to 2 to 3 to 4. It goes like 0.5 to 0.75 to 2. Okay, like it's just kind of all over the place. It's not a uniform acceleration until they get to about here. When you first come out of the starting blocks, your acceleration is kind of all over the place because you're gaining your balance, you're pushing kind of side to side a little bit as well as forward. Your acceleration is very non-uniform for about your first 6 strides. Okay, and then after that, it's quite uniform because you're getting upright and things are moving pretty constantly. And then you get to a point where you just can't run any faster. So you do what? Yeah, you continue to push as hard as you possibly can, but not accelerate anymore. So you travel at your top speed for a few seconds, and then you cross the finish line and not just slow down, but you come to a stop, right? Because your velocity becomes 0 again at the end. Okay, so if you were for any sprint race, this is essentially what your graph would look like. There would be your accelerating phase, okay, which takes up at least half to 2/3 of the race. Okay, and then there's your maintenance phase that is kind of the last third of the race where you are trying to maintain your maximum speed. All right. For different sprinters, their phases are different. Okay. If you got to watch Usain Bolt run, okay, Usain Bolt's acceleration phase is quite a bit longer actually. Okay. He spends a lot more of the race accelerating than most other racers do. Okay, but he has an incredible top speed. Okay, so while some people are able to get to their top speed quickly, the reason they can't stay ahead of Usain Bolt is he continues to accelerate beyond those speeds, reaches his maximum speed at about 70 meters and maintains it for 30. Okay, whereas kind of the shorter, more muscle-bound guys tend to reach their maximum speed by 40 meters or 50 meters, and their maximum speed isn't as much because they don't have as long a legs. Okay, and so they maintain that speed, but it's a lesser speed, and Usain Bolt always seems to reel them in. Okay, because I don't know if you guys remember it, but back in London, he fell. Okay, like he stumbled out of the blocks, had a horrible start, and reeled everybody in and kicked their butt. Okay, simply because he can run so much faster. It's not that he can accelerate faster. He can't. He actually is a poor accelerator, but he doesn't need to be, okay, because he's got such long legs. Okay, when he gets running, okay, one of his strides would cover from like my desk to probably here. Okay, in one stride. Okay, it's ridiculous. Yeah, if you watch him in slow motion when he is at top speed, every step is huge because of how like all he's doing at top speed is basically lifting up his leg and allowing his velocity to carry him forward before he plants it and pulls. At the beginning, short, powerful, but once you reach your top speed, long. Long, still powerful, but long. Okay, and the longer your stride is, the less steps you take, the more likely you are to win. Usain Bolt finishes the 100 meters in I think it's 60. No, he runs it in about like 62 strides. Okay, and most runners take 68 to 70 strides. Okay, like what's his name, our DeGrasse guy, Andre DeGrasse. He's like a 68, 70 stride guy because he's so much shorter, right? Okay. So this is what we were just talking about a minute ago here, okay? The acceleration formula. So this isn't in your notes. You might want to draw this, okay? Acceleration can be calculated from a velocity versus time graph using the slope or using the formula for acceleration. This one here. Acceleration is final velocity minus initial velocity over time, which will be on the formula sheet that I will give you. Yes, it'll be like your periodic table. All right, now we got to look at units. What are the units for acceleration? Meters per second per second. Okay, because when I divide the change in y, okay, the change in y is going to be VF minus VI. So that's going to be in meters per second. When I divide that by time, I'm going meters per second divided by seconds, or meters per second per second. It's telling me the rate at which I change my velocity. This many meters per second every second, you're going that much faster or that much slower. Okay, so if you're falling, you are accelerating at 9.81 meters per second per second. Yes, meters per second over seconds. Okay. We don't ever write it that way. We write it like this. Okay, so when I divide meters per second by seconds, it's like saying meters over seconds divided by seconds over 1. What do you do when you divide fractions? You multiply the reciprocal. So you flip this one over. And what you're left with is meters over seconds times 1 over seconds. Well, meters times 1 is meters. Okay, and seconds times seconds is seconds squared.
Is that MS? M over S divided by S over I?
1, S over 1. Okay, so meters per second divided by seconds. Okay, so we reciprocate and we go meters per second times 1 over seconds, which gives us meters per second squared. Okay, it doesn't mean that we're squaring the number. It means that the seconds are seconds per second, or seconds squared. Okay. All right, so our units for acceleration then are meters per second squared is the way we usually say it. Okay, meters per second is also correct. All right. Questions on the units there? Okay. Anybody need that anymore?
Should we be like calling that one?
Well, I would say the acceleration part, this part up here, yes. Okay, acceleration can be calculated from a velocity versus time graph using the slope, which is the same as using this formula. Well, not exactly the same, but using the numbers in this formula. All right. Okay, so the vertical value of any point on a velocity versus time graph tells us the instantaneous velocity at that time. Okay, we can read velocity directly off of a velocity versus time graph. We can read time directly off of a velocity versus time graph. We can calculate acceleration through the slope of the line, and we can calculate the displacement of the object using average velocity times time, or the area underneath the line. Okay. All right. Okay, I want you guys to try that question right there. Okay, so using the position versus time graph, okay, calculate the total displacements. All right, remembering that, okay, total displacement is final position minus initial position. Okay, we would go final position being 0.5 meters and our initial position being 0.2 meters. Okay, so 0.5 minus 0.2 gives us positive 0.3 meters for our total displacement. All right, everybody follow what I did there? That's about as easy as a position versus time graph calculation gets. Because I suppose in this one you could say forward because it doesn't give you a specific direction. Okay, for part B, the total distance traveled. Well, they go from 0.2 to 1, so that's 0.8 right there. And then they go from 1 back to 0.5, so that's another 0.5. So it looks to me like the total distance should be 1.3 meters. All right, so you got to do a couple of little calculations to figure out each line. Okay, for part C, the average velocity. Well, we already calculated one part of that formula, the total displacement. Okay, so for part C, average velocity, okay, equals total displacement, which you already calculated, over total time. So that's going to be 0.3 meters positive, divided by, that took 7 seconds. Okay, and that should give us 0.04 meters per second, and that is a positive value. right? And to calculate the average speed of the object, same idea, except that it's scalar. So v equals distance over time, and that'll be our 1.3 over 7 seconds, which comes out to 0.19 meters per second. Okay, so is it really any different than what we were doing on that worksheet the other day? Not really, except you're getting your information from a graph instead of from sentences. Okay. All right. So try number 2. If you get done number 2, then you can open up the other worksheet there on the Google Doc from Google Classroom, okay, and view it there.
How do I know whether it's distance or displacement?
From the context of the question. So if it's asking for velocity, you have to use displacement. Okay, and displacement is going to be final position minus initial, always the same. Yeah, and then for distance, it's just figure out how far it goes in all the parts and add them up, regardless of whether they're negative or positive.